It's my pleasure to introduce Martin Makler. I got some notes here for him, let's say. So he graduated in physics at the Physics Institute at the Federal University here in Rio. After that, he got his PhD at the Brazilian Center for Research in Physics, the CBPF, for those who know it, also here in Rio. And Martin has some experience abroad in institutes like University of Arizona, the Fermi Lab. He spent some time at the National Observatory as well, until he finally settled down as a researcher. He's now a researcher at CBPF again. So he came back to his PhD alma mater. He's been there since 2005, and more recently, he's a pesquisador titular. I don't know how to say that in English. Sorry? Tenured researcher or something. I don't know how to translate the term. Martin started his career mostly as a theoretician. So he has some papers on quintessence, Chappelling gas, and theories of dark energy. After that, he finally saw the light, most literally, because he started to study and observe galaxies in the universe. So he's been leading a lot of observational projects in the last few years, still very much related to his research in dark matter, dark energy. He's an expert in the field of lensing, so I'm guessing he'll talk a lot about that. In particular, he's the leader for the SOGRAS, the SOAR Gravitational Arc Survey, and also he's the Brazilian leader of the CS82, the Stripe 82 survey done with CFH-TLS and with infrared telescopes as well. So a lot of those data are being used today for studies in galaxy evolution, and at the same time studies of dark matter and dark energy through weak lensing and strong lensing investigations. And I would think that Martin will show you a little bit of what he's doing in those areas. So without further ado, thank you very much, Martin, for being here, and you have the floor.
Thank you very much, Thiago, for this nice introduction. Good afternoon, everyone. I think it's good, sound, okay. Actually, I'm not gonna show what I'm doing. I don't think we'll have time. Let's see, that's to take care of my time. All right. Otherwise, I'll speak forever, which may happen anyway. So, well, as Thiago said, I'm a researcher at the Brazilian Center for Physics Research, and as most of you know, after the coup, this ministry was downgraded, our institute was downgraded, and so on. So, of course, Faratemia. Okay, so the aim here is really, as the original title, theory meets observations, right? So that was the idea of this course, and you had already 2 lectures by Darren Croughton, right? So I'm giving the second 2 lectures that, as you'll see, should be the first 2 lectures. If we can sort of give a definition on cosmology, cosmology may be defined as a study of structure, evolution, and the origin of the universe. And the lectures you've heard yesterday and on Tuesday were mostly about structure, right? So galaxies and luminosity functions and so on. So today I'll try to focus on evolution of the universe, today and tomorrow actually. And I won't say any word about the origin, but we can take questions. Of course, feel free to take questions at any time. Just interrupt me. I don't stop a lot, so just raise your hand. I prefer not to cover what I prepared and be discussing the questions that you have, okay? Okay, so the challenge of these proposed talks is really what I call phenomenology. So for a theoretical cosmologist, like I used to be, as Thiago said, the universe is homogeneous and isotropic and dominated by dark energy and dark matter, right? So basically, that's it. That's our universe. For astronomers, the universe is full of galaxies, gas, stars, and so on. So how can we connect these 2 pictures? So that's the challenge of phenomenology, is connecting. Of course, it involves a lot of statistical analysis, as you know and as you have seen in the past lectures. basically what we have to do is to do a lot of modeling and include the physical processes, not only dark matter and dark energy, but also the baryons. And a way of doing this is through the semi-analytical modeling that you heard in the 2 previous lectures. Of course, you can try to put this physics on the simulations, like hydrodynamics, AGN feedback, and other physical processes. That's really very, very, very complicated. Basically, we cannot get from cosmology to a realistic galaxy from first principles, right? So that's why we have to do this semi-analytical modeling. But anyway, the aim of this field is really to connect observations and theory and say, well, I have something that I predict from a model, so what kind of observable I can think that I can test my model, right? Or conversely, I'm measuring this, and what does this tell me about some other underlying model? So it really is about making this connection. As I said, this involves simulations, involves statistical analysis, involves, of course, observations, involves theory. So it's really a quite interdisciplinary field, and I think this is very interesting. So just to connect with the 2 previous talks, this is sort of a cartoon of a recipe on how to build a galaxy catalog, right? A catalog of galaxies with their properties. So basically, you have to start with the initial conditions, of course, as in any problem. So this is cosmology, right? So this is the cosmology part of Darren Croton's talk, is I'm starting from cosmology to get galaxies, right? So I need initial data, for example, what's the amplitude of the initial fluctuations and how this amplitude change as a function of size, what we call the power spectrum. Also, what the universe is made of, right? Dark matter, dark energy, baryons, etc. And other cosmological parameters that are connected to the composition and to initial conditions. And for example, like the expansion rate of the universe. That's one of the first things we will see. So given the composition initial conditions, I can run machinery, which means the equations of general relativity, the transport equations of all the fluids involved, statistics, thermodynamics, particle physics, and what is simple of the early evolution of the universe is that everything is linear. And next talk, so tomorrow, I'll discuss a little bit about this. And from this, you can obtain observables, for example, like the cosmic microwave background. But what the 2 previous lectures were really focused on was the nonlinear evolution, which basically the only way to handle is going through very large simulations and body simulations, and then processing these simulations through some semi-analytic modeling that now you know very well what it means. You have to also do some selection function to try to reproduce what your data is. So you have a magnitude limited catalog, you have a finite angular aperture, field of view. You may have, if you want to add to this realistic features in images, really to have a mock image. So the ideal case would be that I'm comparing my very theoretical things with a real image, right? And making, to go all around from the image to the theory and or backwards, we have to go through this process. So today's talk will be only focused on this side, composition of the universe. And tomorrow's talk will be based on the linear evolution, just to make give an idea. So Darren's, one of the first slides by him was this, was what we call the cosmic pie, the composition, dark energy, dark matter, atoms. So most of my talk will be dedicated to try to get to here. So how we got to this composition. And tomorrow's talk, my goal will be to get to this, how we get the linear fluctuations and how we produce a plot like this, a cosmic microwave background. And if I have time, I will discuss a bit how this propagates to large-scale structures, and also, if I have time, mention on lensing. Let's see tomorrow. A second goal of the talk is try to understand plots like this. So cosmologists, 99% of cosmologists, they are always showing plots like this, when you have some omega matter, some W, or variants of this, is level curves. So I want you at least to have a glimpse on what do these parameters mean, right? Any questions so far? Okay, so that's the summary of the today's lecture. So basically, I'll discuss the cosmic pie, right? So back to the basics, right? You had this very advanced talk on galaxy formation. Now, okay, what produced all this? And I'll try to really do like a worked example. I will not go through all the calculations, but I really try to go through a complete loop from something that connects a model to something that can be observed, which will be the cosmological distance, the luminosity distance, and what we get from supernovae, right? So we'll talk a little bit about dark matter, expansion of the universe, get to dark energy, and if we have time, we'll discuss a little bit about the thermal history of the universe, and tomorrow, CMB and other observables, and we'll see what we can do. So first, Dark Side of the Universe, episode 1. Oh, I'm sorry. So I did not translate this. Okay, so it's by Alberto Calheiro, who's a heteronym of a very famous Portuguese writer, Fernando Pessoa. So the only mystery of the universe is not the more, but the less. What exists transcends for me what I think exists. So I like this because my interpretation connects to dark matter and dark energy, right? Okay, so let's first evidence for dark energy. Everyone knows what a galaxy cluster is, right? You have all these galaxies going around. They are bound by the gravity of the cluster itself. The galaxies have sort of random motions, the theorem. I guess everyone knows what the Veil theorem is, but if someone doesn't know and if it's not shy, please shout. Okay, good. So this is the Veil theorem. Sometimes we learn about this in undergrad courses, in physics, I guess in astronomy always, in physics only sometimes. But anyway, so the kinetic energy of a system of particles that are gravitating is twice the potential energy. So if we have, and what Zwicky did in 1934, you measure the redshift of many galaxies in a cluster, so you have the velocity relative to the mean velocity of the cluster. So you're able to get a handle on the kinetic energy. So that's what this plot is showing, right? So this is the velocity of each of these dots is a galaxy within a galaxy cluster, right? And this is the angular distance from the center. So you see that galaxies have really a velocity dispersion, and there is a mean velocity, which as we'll see is just the velocity of these clusters with respect to us, right? So this, the universe is expanding, the cluster is receding from us, and we can measure all these velocities, so we can have a handle, at least on the velocities of this side, and if we measure the velocities, we can have a handle on the potential, right? So let's make a very, very broad assumptions. Everything, of course, we say in this kind of courses is very superficial, very simple, because what we can say in a couple of minutes, right? But please be sure that we do the back of envelope calculations to have order of magnitude estimates, but then everyone works down with a very detailed example, right? So what I will try to show here is based on these 3 lines, but of course the problem has been and is being always studied in a lot of details with simulations and so on. But just to have an idea of what's going on, let's do this. Okay, the kinetic energy is the sum of kinetic energies of each of the galaxies, so mass of a galaxy times its velocity squared, and the potential energy. We'll think of this cluster as a round thing, so we take the potential of a sphere, right? Okay, so this side is the kinetic energy, and this is half the potential energy. Right, so let's, for now, assume that all the galaxies have the same velocity. We see that this is pretty bounded, so we can have an estimate. Here's something like 2,000 kilometers per second. So if you assume that all the velocities are the same, here's the mass, so you can have an estimate of the mass. So this back of envelope calculation tells you that the mass is twice the radius times the speed with relative to the mean over g. Fine, that will give you an order of magnitude estimate, very broad. But when Zwicky did that, and what he compared to what? He compared to the luminosity of the cluster. So, okay, let's assume that everything in clusters is stars. Let's take the mass to light ratio of the sun. So I will measure the total light flux. So I will weight by the mass to light ratio of the sun, then I can get a mass. So if I assume every single thing that shines in the cluster is our sun, we'll give you a mass based on the mass to light ratio. And this mass compared to this one has 2 orders of magnitude difference, right? It's not a factor of 2 that can be accommodated very easily, not a factor of 5, not even 10. It's a factor of 100. So that was very shocking. That's how Zwick introduced the notion of something dark that you cannot see, and that's what's made of most of the cluster. So basically, clusters need much more mass to hold the galaxies. If we just use the mass, using these mass to light ratios, the galaxies would just fly away, right? So that was the first evidence for dark matter. Again, looking at clusters, clusters happen to have a very, very diluted gas all over the cluster, but this gas is very hot. Temperature is about 10 million Celsius. So it emits and emits in the X-ray. So think of this gas in the cluster as a gas in hydrostatic equilibrium. You can easily show that, so this is the hydrostatic equilibrium equation. Take some very simple monatomic gas, and you can work out the temperature. So how the temperature depends on the density. So an example, if you have this ideal monatomic gas, you have that the density has this dependence on the temperature of the gas. So here's the electrons, the mass of the electrons. So basically, if I measure temperature, I can have a handle on the density, and if I integrate the density, I have the mass, right? So I can measure what the mass that gravitates, because it's here, right, in this side of the hydrostatic equilibrium. So the mass that gravitates is given by this, right? I can compare this to the mass that is emitting light just by measuring the flux of light. So I know the temperature, so the total flux in X-rays will give us also a mass, but the mass of what's shining. And here is the contours in the X-ray. So you already see that the gas is much more less concentrated than the galaxies. Galaxies are really concentrated. Light is concentrated in galaxies, and then the mass in gas. Most of the mass in the cluster actually is in the gas. So this light reflection predicted by Einstein makes many effects. Of course, you see the light, if we are here, there are multiple images of the same source, right? Why I know it's the same source? There are many ways of knowing, but if you have a spectrum of them, there's no doubt about. So these are multiple images of a background source, and you can use these multiple images as they should be only a single image. You can use these multiple images, modeling this object, to have the mass of the cluster. And again, that shows you that most of the mass is in form of something that we don't see in X-ray, we don't see in the optical, and we don't see in any wavelength, right? That's another example of a strong lensing system, that 1689. So you see these arcs and a lot of little arclets. So if you pay attention of background sources, that you can measure statistically in many objects, even if you cannot see by eye in this object. And again, you can use weak lensing to weight the systems and measure the total mass, which is higher than the mass in light and the mass in stars and the mass in gas. And again, what you see is that there is an overall potential here producing the weak lensing distortion, right? So the dark matter is much more smooth than the galaxies. Already the gas is more smooth than the galaxies, it's all over here, and the dark matter too. So we introduced the concept of a halo, a dark matter halo. So each galaxy has a dark matter halo that goes beyond what the light visible radius is, but also all this cluster is embedded in a big dark matter halo. Okay, so this example, this case became very famous 10 years ago because it's a merging cluster. And merging clusters are very interesting because, you know, as I said, clusters have the galaxies, which you see stars. It has the gas, which is more uniformly distributed, and you have the dark matter. When two things like that collide, you have a segregation between these components. So it's really a perfect example where you want to differentiate how they behave, right? Also, an alternative to having dark matter is, or was, or okay, so an alternative to having dark matter is just to modify gravity. So a theory, a model, or, well, I don't even know how to name it, but an alternative was modify Newtonian dynamics. So you're saying, look, the gravity is modified, and it's all produced by baryons, right? Okay, so fine, it could be. So the gravity is where the baryons are. It's just that it's modified. It's not like Einstein equation. It's something else. Okay, so when you have this collision, what do you expect? You have here something that has gas, dark matter, and stars, galaxies. Here, mass, gas, galaxies, dark matter. So that's option 1, where there is dark matter. Option 2, no dark matter. There is only gas and galaxies here, gas and galaxies here, okay? So let's see what happens without dark matter, because it's simpler. You have the gas and the stars, the thing collides. Okay, the gas interacts, of course, so it's sort of in the middle. The galaxies go through, right? So the gas is in the middle, the galaxies are here after the collision. And if I measure a lensing signal, where the lensing signal should be? Where most of the mass is, because there is no dark matter, right? So where the gas is. So the lensing signal should be somewhere in the middle, where there is gas, because most of the mass in the clusters is made out of gas. Now let's think that there is dark matter. So dark matter, galaxies, gas, dark matter, galaxies, gas. The thing is, dark matter doesn't interact. So the galaxies go through, dark matter goes through, as with the galaxies, and the gas sets in between. What's the difference? The difference is that most of the mass now is where the galaxies are, because most of the mass is dark matter, right? So if you measure a lensing signal, it will be where the galaxies are. Okay, so people just went and look at it. So these are galaxies, here are the galaxies. So, okay, you see a configuration post-merging. And this green contours is where the lensing is. So clearly, there are two two mass components, or don't call it mass for now, just two regions where the lensing signal is concentrated, right? And now if you look at the X-ray, where's the gas? Sort of in between, as you expected, right? So if you see, you look at the peak of the gas concentration, and you compare with the peak of the lensing signal, you see a big shift, and this was considered a very strong indication for dark matter. Now, many of these systems have been observed, many, like about maybe 10, okay, this is became something usual. But what's very interesting now is that, okay, dark matter, as I'll show during all this talk, interacts very weakly. But still, we can try to measure this weak interaction of dark matter, for example, with itself. And we are, again, using these merging clusters, but now to look at the segregation of the galaxies from the gas, which is, of course, should happen, but also galaxies from the dark matter, right? So we can leave this for questions for today or tomorrow. Any questions so far? Yeah. You need a microphone.
My question was, because you say that there have been tens of such systems that have...
Yes.
That at the beginning, it's important to, verify that this is not a freak. Maybe there's some interest in the orientation, geometry, but
yes.
I keep on hearing, reading proposals or something, I'm reading papers, it's like, oh, this is like the bullet cluster.
Yes.
Is it still interesting to continue?
Finding this, yes. Because I said 10, I was even exaggerating. I'm personally aware of less than 10, but maybe 6, 7. So yeah, there are still interesting systems to follow up. To the detail that the bullet cluster has been studied, there are very few actually. So if you really want to do this study detailed, you want to have the redshift of all the galaxy cluster members to do the sort of virial type analysis. You want to have a deep and high quality imaging for the lensing, and you also want to have X-ray. So this combination of 3 is not available for many lensing clusters. It's just less than a handful. So it's still interesting, and also you have these head-on collisions. You have these collisions that are perpendicular, and also some of the systems show offset of the matter relative to galaxies, so they're interesting for self-interacting dark matter. Some are not, so I think it's still fashionable or still worth studying these systems in detail. Yeah. Yes.
So the fact that if the gas would have not been there, you would have concluded that it's not driven by dark matter. But there are a few things that I would like your opinion on. For example, is it known how much time in the past the merging has occurred? Because this can distort the internal distribution. Gas could come from the internal galaxy, not only the intracluster medium. And that, to me, logically would fall into the center, simply because you have, and you said you go through. So there will be idle things independently, and that would work in both the scenario. So what is your opinion on the exclusion of the first?
So this dynamical options are in detail. So first people try to with n-body simulation. Yes, there's a nice paper. Okay, so they okay. So how can I reproduce these configurations? So one of the ways to really do simulations, and if you happen to reproduce the system, also you learn about the initial conditions, the time of how this has happened. But also people study the tidal effect. So this have really been looked into a lot of detail, not only like this paper, first one, which is basically what I just said, but there are lots of papers on systematics and studying all these alternatives. Especially now that there is this indication for self-interacting dark matter, which is something quite strong. So people are looking, okay, is this really, okay, basically that this is a result of a merging, I think it's sort of no one argues. But on the details of the physical processes that produce this, there has been quite some discussion, yeah. Also, I must note that people try to reproduce this system with more exotic modified gravity models, like the TeVeS, for example, is tensor vector scalar gravity. I don't think it's very beautiful in the sense that you need, besides general relativity, which is a tensor, you need a vector and you need a scalar, and you need a Lagrangian for the vector and a Lagrangian for the scalar. So it's a lot of physics, right? Having one single dark matter seems simpler. But anyway, let's not apply the Occam razor principle now. Let's just think I have a more complicated gravity theory. So they try to reproduce the system, and it's fine if you add neutrinos that are quite heavy for the bounds today. So you still need to put something like neutrinos, not warm dark matter, and not dark matter, neutrinos, but these neutrinos are heavier than what the bounds are. So basically, even if you try, at least for now, the sophisticated modifications of gravity, they are on the market. They don't seem to work unless you make other sort of bold assumptions. I like this example because this is a single cluster. It's a relaxed cluster, so it's sort of a simple, where you have the combination of these three measurements. So the weak lensing ones, which are the red ones, the gas, which is the contours in green, and of course you see the optical here, and you have virial masses. And all these three estimates agree within 20%, right? And again, mass is less concentrated. I'm always repeating this, and if I don't say why, then ask me why I'm repeating this all the time. But it has to do also with the beginning of the talk. Okay, so this was, all I said is in galaxy clusters, right? But this goes down all to dwarf galaxies. So in also a historical example, this was studied by Vera Rubin in the 70s, and it gave a lot of strength for the dark matter. So Zwicky 34, but really, you know, okay, there was a curiosity. After Vera Rubin's works in the 70s, this became really an important thing. And what she did, she studied spiral galaxies for which you can trace a rotation curve, so velocity as a time of as a function of distance. And again, let's do a very simple back-of-envelope calculation just to have an idea. Let's think that I have a star here in the galaxy, right? So it's just following the potential here. So it's a circular motion. So, okay, here is the gravity acceleration of this particle. And the gravity acceleration must be the centripetal acceleration, right? So the centripetal acceleration is given by the speed. And here's the mass of the galaxy. So if you do this, if I'm very far from the galaxy, most of the mass is concentrated here, so the mass is constant, right? So I expect that the speed will go with 1 over the square root of r. So I expect that the stars far away from the galaxy will have this kind of drop in the rotation velocity, right? Actually, we don't see a lot of star here, so you see the gas in the outskirts, right? But what people measure is this. So the rotation curve doesn't go down, and even when you go very far, more than the optical radius of the galaxy, you still see not going down, but you see the velocities constant or going up. Or, I mean, they're, you know, that's definitely they are not decreasing. So again, if you think that this is in a larger dark matter halo, and if the density is just like 1 over r squared, such that the mass increases with the radius, you get that this velocity is constant, right? So if the mass here of something that weighs more than stars goes as a function of r, the mass is proportional to r, density 1 over r squared, then you get a flat rotation curve. Okay, so it's again an evidence for dark matter. And of course, in the galaxies, the fraction of dark matter is less than in the clusters, because dark matter is less concentrated. Okay. Okay, so just a brief recap on the evidences for dark matter. We spoke about galaxy rotation curves. Actually, in individual galaxies that are not rotationally supported, like in early type galaxies where you have video velocities, you can also have an estimate of the mass just by the velocity dispersion. And again, you get the same result, that there is more dark matter than visible matter. So it's present down to the galaxies, even dwarf galaxies, to the clusters. So motion of stars in galaxies, motions of galaxies in clusters, and also the large scale structure of the universe. I haven't shown that, but you can connect motions relative to the average expansion of the universe. Motions relative to this average expansion, we call these peculiar motions, and you can relate the peculiar motions to the mass. And again, even looking at the very large scale structure of the universe, you measure the quantity of mass, and it has to be more than the gas and stars and so on. So there is also evidence from large scale structure. Also from the X-ray flux in clusters, as I mentioned, from gravitational lensing in all the scales, from galaxies to galaxy clusters to large scale structures. I didn't speak about the Sunyaev-Zeldovich effect today, so just keep this strange name in mind, that I'll mention it tomorrow. But it's a distortion that the galaxy cluster produces in the light of the cosmic microwave background, and again, it's connected to the mass. So all these things point through that there is 5 times more dark matter than what we call standard matter, right? For physicists, what we call standard model particles, particles that are made out of quarks, or electrons, or muons, or everything that's in the standard model. So there is 80% of the mass is in the form of dark matter. Okay, it does not interact with light, otherwise we would see it, otherwise it would be able to cool down by emitting photons. One of the evidence it doesn't cool down is it much more dispersed. Why it cannot concentrate? Because it cannot lose kinetic energy. So that's more difficult for it to lose kinetic energy. So that's why it's more dispersed. So it doesn't have electromagnetic interaction. But also when we study the early universe, and we'll see this for sure, it will be tomorrow, one time today, yes? Tomorrow, when we see the early universe, we'll study nucleosynthesis. So dark matter cannot participate in this process. So dark matter cannot have the strong nuclear interaction, right? So in terms of particle physics, it cannot have electromagnetic nor nuclear interactions. It can only have the weak nuclear interaction, and of course, it must have the gravitational interaction, right? On the one hand, everything we know has gravitational interaction, and on the other hand, that's how we detect it. So in principle, besides gravity, this particle could have weak interaction, right? This interaction that's connected to some nuclear decays and so on. And a lot of experiments now are running trying to measure the weak interaction of the dark matter in detectors, right? So there are about 10 of these detectors functioning that they, with different processes, they try to detect scattering of the dark matter with some nucleus of some detector, right? Also, there are searches for dark matter annihilation, as dark matter may annihilate and emit, for example, X-ray or gamma rays. So there's a lot of searches for the evidence of the dark matter in annihilations, in the high energy astrophysics, and also in accelerators. If you happen to produce some particle and there is something that you do not detect on your big particle detector, like in the LHC, this missing energy may be in the form of producing some dark matter. So you look for dark matter by annihilations, you look by indirect detection, by scattering of a detector, you look at by direct production, and of course by all this lensing evidence that I have shown. So far, the only direct indication of the presence of dark matter is from astrophysics, although people are very hopeful to detect. That's why they put money on detectors. And how about the ordinary matter? 10% of it is stars. And most, of course, is gas. Gas in the galaxies, in the intracluster medium, in the intergalactic medium, in the intercluster medium, and all around. Okay, so just to end this first part of this talk, so the matter is the component that clusters, right? The one that produces gradients of the gravity field, because everything I mentioned is based on that. So of the matter that clusters, the dark matter dominates the energy density of the universe. And the universe is more homogeneous than what it seems when we look at dark matter, right? Okay, any questions so far? And I'm very happy to take questions in Portuguese, of course. I can translate them, no problem. But I'm happy to take. Okay, so this dark matter. Now let's speak about the dynamics of the universe. Of course, you all know the universe is expanding, but let's look how this was discovered, and we'll connect this to models. So translate the universe is not my idea. My idea of the universe is which is mine. So it's just I'm just quoting this from the same poet, Fernando Pessoa, which means we do models, right? So my conception of the universe is mine. We do models. But the universe is out there. So what we have to do is to test our models with reality. We always have to do this reality check. And I can give a counterexample in my department privately, just to make some fun. Okay, so Doppler effect. You all know what Doppler effect is. It affects sound, it affects light. You know what blue shift is, red shift. And each time I say something you know and you don't, please just say, I don't, and there's no problem at all, right? I know the audience is very, very broad. Some are not from physics, some are undergrads. So just say, I'm just assuming you know, but if you ask a question, that will help maybe others that are more shy that they don't say, right? So it's my fault if I'm not explaining something. So please stand up. But okay, anyway, so this is a cartoon about the redshift. Some object is emitting some light, for example, and as it goes on, the center changes. If the object is coming close to you, it's a blue shift. It's going in your opposite direction is redshift. And here's the expression, right? The fractional variation of the wavelength as compared to the rest wavelength is given by this expression, right? We are usually, in undergrads, we only see this part, v over c, so the speed of the object relative to the speed of the wave. In this case, is the sound. And this makes a lot of misconceptions, because people say, look, if you have redshift more than 1, it cannot be a speed, because the speed more than the speed of light doesn't exist. So the fact that you have redshift more than 1 tells you that the expansion of the universe is not a velocity. This is bullshit. I'm sorry. The real thing, I mean, even in special relativity, you take any two observers. You don't need to make any assumptions of any whatever. Just take two observables that they move relative to each other, and you obtain an expression like this. Even in general relativity, the kinematics connecting the light emitted by an observer and received by another observer is this. So you see that as velocity approaches velocity of light, this goes to infinity. Okay, so if you happen to see a redshift higher than infinity, then I believe you that's not a motion, okay? This is, let's take a reference spectrum. Imagine a galaxy that's not receding from us. Here's observed spectrum, and the redshift, of course, you know, is a variation of the position of the lines, right? So this is what we define as redshift, is the wavelength of the light received less the emitted one divided by the emitted one. And of course, we measure this, determine some lines in the spectrum. One of my aims today is try to connect this thing, which is an observable, to something that's part of a model, right? Doing this phenomenology. So far, I just said regarding expansion of the universe, well, I didn't say anything, but we'll measure redshifts. But how this redshift connects to a model, that will be one of the things to achieve today. Okay, so expansion of the universe. 1912, Henrietta Leavitt, that's a long story, but she was studying some specific time of variable stars, which are Cepheids, and they happened, the period of the Cepheid correlated very well with the intrinsic luminosity of the Cepheids, right? So she discovered this period luminosity relation, which means that I can turn the Cepheids in standard candles, right? Why do we need standard candles? Let's think that I have a room here full of light bulbs. right? But you have light bulbs that have 20 watts, 60 watt, 80 watt, and so on. And I, of course, don't have two eyes, because otherwise I can use my parallax. Let's think I have one eye only. And I have all these lights. How can I know if one of these lights is brighter because it's closer to myself, or is brighter intrinsically, right? So if I see a fainter light, is it faint just because it's 20 watts, or is an 80 watt bulb, but it happens to be in the end of the room? I cannot know, right? But if somebody tells me, look, this bulb has a label, it's a 40 watt label, then I can measure the flux here, so I can measure the number of photons per unit area of a given energy, right? And I can compute by the square, 1 over the square of the distance, and I can say, well, that's the distance of this light, right? So as you know that the light, the flux of light goes 1 over the square of the distance, if you know what the total light emitted is, you know very simply how to compute distances, just measure a flux, right? So that's why the standard candles, they are very important in cosmology, because you cannot just go and take a ruler and try to measure a distance, right? Within the galaxy, with closer stars, we can do parallax, but not with distant galaxies. So this was very important, because you could detect then DCFAs in other galaxies and use them as standard candles and measure distances. Vestus Lieffer in 1917, he was looking at spectra of galaxies. Of course, he had the most powerful telescope of the time to be able to get enough light to measure spectrum, of a galaxy, right? And he measured spectrum of 15 galaxies. And out of these 15 galaxies, he could identify, of course, like hydrogen lines and so on. So he could measure the redshift. And out of these 15 galaxies, 13 were receding from us. Well, you see, if the universe is static, there should be no redshift. But maybe there are some random motions like that, and you would have sort of half of the galaxies are getting close to us, half are getting further away, and that's it. But not like really, galaxies were receding from us. That was sort of a big surprise, at least for. Okay, here you don't know the distance. So the only observation was that the dimmer the galaxy, the quicker it was receding from us. But then in the 1929, Hubble combined these two information. So he used the standard candles, C-fades at standard candles to be able to measure a distance. Here is in 2 times 10 to the 6 parsecs, right? So 2 megaparsecs. And he used the spectrum, the data from Lieffer and other data, to measure the receding velocity. And the receding velocity is 10,000 kilometers. That's the way it's printed out in the original paper, right? 10,000 kilometers. But of course, it's 10,000 kilometers per second. And so he saw with a bunch of points that there was an approximate relation between distance and the redshift, right? And he writes in the paper, and thanks to NASA ADS, all these papers are available online. He writes in the paper, there is an approximately linear relation between the distance and the velocity, which may be connected to a relation obtained by De Sitter. So De Sitter used the general relativity to obtain a relation between the speed and the distance, which of course was the expansion of the universe. But he didn't write like, I discovered the expansion of the universe. So to try to understand, I had something very, very, very modern of 2 slides in a piece of plastic, but it happens that we cannot project this anymore, so let's do it with this. So okay, the expansion of the universe is homogeneous and isotropic. So let's imagine for a moment that all galaxies, they are distributed in a grid, right? So the distance between these 2 galaxies is the same, right? If the universe is homogeneous, that means that the velocity from this galaxy to this one is the same as the velocity from this galaxy to this one, right? So no galaxy is in the center of the universe. But if this galaxy to this one is receding at velocity v, with respect to this one goes to v, right? So that's very easy to see the linear relation. If everything is expanding all together, the relation has to be linear, which is exactly what Hubble saw. You may ask deviations of this linearity. Any question about that? Okay, we'll have reasons why we'll deviate. But at first, for local galaxies, which are far away than our local group, that are receding with the expansion of the universe, we see a linear relation that's very easy to understand in terms of an expanding universe, right? So the expansion is homogeneous and isotropic, so it does mean that there is no center. We see all galaxies receding from us, but if you happen to be in another galaxy very far away, you see everyone receding from it, right? So there is no center, right? So there are a lot of animations that show the Big Bang as like an explosion, right? So there's no explosion. There is no prefix X. That's not outside the universe, right? The universe, as far as we know, is everything we know. It has no borders, so there is not explosion. In English, it's Big Bang, right? Some people in Portuguese translate to grande explosão. That's wrong. So it's we call grande estrondo or kaboom or anything like that, right? Okay, so this Hubble was 2 megaparsecs, right? So many years later, in 2001, that was the outcome of one of Hubble Space Telescope key projects. This is 600 megaparsecs. Hubble was 2 megaparsecs. This is 40,000 kilometers per second. And Hubble, I forgot, was something like 2,000. So okay, so this is, we continue to see the linearity of the Hubble law very well. This is a 10% measurement. And okay, just to recap again, you know, the expansion, as far as we know, is homogeneous and isotropic, so it's the same in all directions and in all positions in the universe. It's not an explosion. And the linear relation is this. It's not a law like Hubble law. As you will see, this is just an approximation of many other things. But there is a linear connection, and this linear factor is called the Hubble parameter, and we usually write it that way. During a lot of time, we had a lot of uncertainty on how to measure the value of h. So you say, okay, let's call the Hubble parameter 100 kilometers per second per megaparsec times h. So my ignorance in h naught is in the little h. It's nice because little h is, doesn't have dimensions, and everything we do in practice when we compute doesn't have dimensions. So we need to have something with no dimensions. We do a small h. So in the Hubble time, h was 5, right? Now it's 0.70 something, 0.60 something. Why? Because there's well, there were two types of Cepheids. That's a long story. And this is just to tell you two things. Always that we are always oversimplifying things when we tell them in one lecture. So there are much, much more details. And also that there are systematic errors, okay? This is very important. You may have a measurement, and you're very happy because your error bar is very small. But you need to try to think about what possible things are biasing your results. Some possible physics that I'm not considering, some possible observational effects, some population effects, some selection effect. That's why most of the good papers, usually in astronomy and in cosmology, they spend more time doing the error bars and the systematic uncertainties than just measuring the quantity you want to measure. That's a Hubble diagram in the last year's version. This is a plot by Adam Rees, which you know, Nobel Prize winner. This is the sort of the Hubble expansion corrected by some things that we can discuss if there are questions. But basically, you linearize the expansion rate to have the projection of this line will give you the Hubble H naught, the Hubble factor, right? And if you do this correct scaling, you see this very, very good relation with a lot of galaxies. So the current value using one set of observables is 73 kilometers per second with a 2% uncertainty, which the authors discuss in a very lengthy paper, includes also the systematic uncertainties. And just to give a very little taste of how complicated things are, of course, you cannot just calibrate our standard candles. As I will mention, one of the standard candles are type 1a supernova. I'll discuss more about them. But it's not just the supernova gives you a distance. First, you want to do parallax with nearby galaxies, you know, geometry. I'm the sun, here's the Earth. The Earth looks at the nearby stars. After 6 months, it looks at nearby stars again. They happen to be moving with respect to further away stars. So by parallax, you can measure distance very precisely nowadays with Hipparcos, with Gaia, and so on. And you can calibrate other distance indicators, like the Cepheids. And then you can use the Cepheids to calibrate other distance indicators, like supernovae. And then you can use supernova to do a Hubble plot and get the expansion rate of the universe. So, of course, this is what we call the cosmic ladder. It's one way of measuring the cosmological expansion. There are other ways that doesn't rely at all on this ladder, and they get the same numbers. So I can show plots if you ask during the questions. Any questions so far? Tomorrow, very briefly. Okay, so now let's connect this with models, right? And I'll try to make this work at example, but I'll go really fast. So my idea is not that you'll be able to follow all the calculations, but you'll be able to follow the idea, and you can take these slides, and if you want, I have an exercise list that you can do. So the idea is that you won't follow all, but you have a rough idea, and you can work this out during the weekend, for example, right? So the universe is homogeneous and isotropic, so I can choose any piece of the universe as the center. So let's choose this part. And of course, as it is homogeneous and isotropic, I can take any point here, and I'll have spherical symmetry with respect to the center, right? So take a little piece of matter here, which is sitting at the distance r. So distance little r here, right? Is the little r that appears there. So this is a volume element in the expanding universe, and it will have a mass small m, right? Okay, and I will write the dynamics of this thing as, okay, so this is big R. The separation between these 2 points, this arbitrary center that I chosen, and this element of mass, the distance between them will be given by big R, and I will write it parameterized like that. So big R as a function of t is a function only of t and r, right? So the r just doesn't change with time. It's just an initial value that I have chosen arbitrarily, and what I want to know is how a changes with time. So what I will write there, starting with Newton, is the energy conservation equation, so the kinetic energy of the particle, right? The potential energy. So if we are with this symmetry here, we know by Gauss theorem that what's outside this radius does not contribute to the gravitational potential, right? The gravitational potential is given only by the gravitational potential of this sphere within the distance r. So this is my gravitational potential, and this is the total energy, so connected to the initial condition that I give to this particle. So now I divide everything by little m here. I use this expression for a, right? And I will have that a dot squared. Here, the mass, what is the mass? Is the mass enclosed in this radius, right? So this big M is the mass here, which is 4/3 pi cube of r squared, right? So if I replace this, I will have here the density. So it's the volume times the density, 4/3 pi big R cubed times the density. And you'll see here that the factors of m, little m, cancel. The factors of, not cancel, they are the same. So I divide E by little m. I have r square here, so I divide everything by r square. So on the left side, I have something that depends only on A, right? And A is a function only of time because the universe is homogeneous. And the density is also a function of time only because the universe is homogeneous. And what's left here is something that's E over little m over 2E over little m over little r squared. So this is something that depends on the distance. But here is only something that depends on time. Okay, so this, what I will do is, okay, so each shell will have this quantity E that is given in terms of m and r. But what really matters is the combination of E over m and r squared. This thing cannot change, right? This thing here, what I call k, has to be the same because these are only functions of the time, right? So I write an equation by only using Newton theory and the fact that the things should be homogeneous isotropic. I can write this equation here, right? Okay, so this you can do on the back of envelope. But this happens to be the right equation for the expansion of the universe. So if I know the density of the universe, this tells you how the A changes. And the A tells you how all distances change. If I now write an R2 here, big R2, so two other objects very distant away, but they all scale by the same A. So A is the quantity that scales all the distances, right? As we saw in the previous example, if you have two objects separated by some distance and the factor A doubles, it will double. If the other object is very close in an homogeneous universe and A doubles, also the distance doubles. So A will be the scale factor for everything, right? And the evolution of A tells how the universe evolves. Any questions so far? We can have some very simple examples of this equation just to have an idea, right? Let's take particles, for example. Particles, if this is made of particles and the volume increases, right? So this little big R and little r, they increase. The density will decrease because the particles will get more diluted, right? So the density of particles is inversely proportional to the cube of the distances. So I can plug this here, so it's for particles. And if k equals 0, you can find very easily the solution. It's a to the 2/3, right? So it means that all distances scale with the time to the 2/3. And this is a very well-known solution because called Einstein de Sitter solution. It's a universe that has we'll see that this k is connected to curvature. So it's a universe with no curvature, only dust, only matter that doesn't interact, only particles. It evolves like that. If k is not 0, then you can have these plots like here. This is k equals 0, t to the 2/3. If k is larger than 0, the universe may recollapse. If k is smaller than 0, then the universe will continue expanding forever, but it's not 2/3. Okay, something very important. We speak all the time about Big Bang, beginning of the universe, and so on. We really don't know, right? Because we extrapolate the solution that we get from this equation here. Oops. We extrapolate the solution that we get from this equation here with some matter content, and with this matter content, it shows you that scale factor goes to 0. If this scale factor goes to 0, density goes to infinity, temperature goes to infinity. However, we don't know what kind of matter happens when you have very, very high densities. So, and whether, gravity, we know it's not a quantum theory, but of course the word is quantum, so we don't have a final theory of gravity and so on. So basically we cannot tell what happens when the densities are very huge. So basically we should just take this point. We don't know if there's a single or not. What we know is that we can go down to the very remote times and we can follow this history very, very well down to some beginning. And what I'll call beginning is just an extrapolation. This curve, you can mathematically extrapolate and you find a t0, right? So everything I will refer to is to the beginning of time in the sense that I have these curves and I can extrapolate to some beginning. I will not discuss the origin of the universe, whether there is a beginning, whether there is a bounce or anything. I just say we can understand very well the history of the universe down to very, very high densities, and we can just extrapolate and say, well, this time equals 0 for me, right? So that's a nomenclature clarification. Okay. I'll go this fast because I don't think I have a lot of time, so don't be sad, but I will skip a lot of equations, and I'll tell you the final thing. But it's very, very simple. You just look at the energy conservation, good old energy conservation. You know that the energy is conserved through this. You look at the energy densities in an expanding universe. You also think of rest mass and the conservation of rest mass. And always recall that when we are referring rho as a density, it's a total density, right? It's a density on the relativistic sense. It includes the energy density, the mass density, and the internal energy, right? So you can write the energy density and the pressure and the scale factor of the universe only using thermodynamics. They are connected by this equation, right? And I'm always like people, I do C equal 1. Otherwise, it's rho over C squared, P over C squared here. Okay, so this is each fluid. I said that there is dark matter, there is gas, there is many things. So the universe has a lot of composition. We know there is light, there is neutrinos. If we put all these components, they don't interact between themselves. So I put a little I here. If they are all conserved, non-interacting, we have one of these equations for each component of the universe. Dark matter will obey this. If there is dark energy, will obey this. Anything that we know will obey this independently. But we need some equation of state connecting the pressure and the density to be able to solve this equation. What means solving this equation? Means knowing the density as a function of A, knowing the density as a function of the scale factor of the universe. This is solving this equation. But to solve, I need a connection between pressure and density. And for example, the first example we saw, if just particles, non-interacting particles, pressure is simply 0. So if the pressure is 0, you can solve this equation easily, and you get this rho to the minus to the minus 3, right? Another example is you take radiation. Everyone knows that pressure in the radiation is a third of the density, C equal 1 again. So I can plug this third here, right? So it will be 4/3. Here will be a 4, and you can easily find that the exponent will be 4. So the energy of the radiation, like light, for example, electromagnetic radiation, will go with the A to the minus 4. And you know, this is Stefan Boltzmann law, if I remember. Well, in any case, you know that the energy density of light for a black body is connected to the temperature with the temperature to the 4th. So this tells you that if the universe has some black body radiation, right, just thermal radiation, as it expands, as the density of radiation goes to the A to the minus 4, that means that the temperature of this radiation, which we usually call temperature of the universe, goes with A to the minus 1. A is the scale factor, right? Another example, very fashionable nowadays, is a vacuum. So if you look at the vacuum in the sense of the particle physics, in the sense of quantum field theory, the vacuum is an equation of state. It's P minus rho, right? Another way of looking into this is that you can momentum tensor and make any kind of Lorentz transformation, and the only energy momentum tensor that doesn't change through this Lorentz transformation, so it's what we would call vacuum, everyone sees the same, has to have this P is equal minus rho, right? So in this case, this is constant, of course, this is 0, of course, and then the rho is 0, then it's constant. So each of the components of the universe evolves with the scale factor in a different way, right? What gives us the total matter energy in the universe is the sum of everything that's inside, right? So it will be a sum that changes with the scale factor. If I now want to know the dynamics, so how the universe evolves, not only I need to know how each component evolves with A, which I take from the energy conservation, but I need to plug this into the Friedman equation to have A as a function of T, right? So one example that we saw before, well, we didn't see before. So one example, if you take K equals 0 here, so we'll see that this is connected to the curvature of the universe. K equals 0. Radiation, you get this. With matter, as we saw before, is 2/3. If we get the vacuum, vacuum means rho equal constant, right? So this is constant. So A dot over A is a constant, and you have an exponential, right? So that's why people say that you have an exponential expansion when you have a cosmological constant or dark energy, right? And if I have a universe that doesn't have anything, that we call a Milnor universe, then A is just proportional to the time, right? Also, there are things that are worth mentioning as we are dedicating a lot of time to this. Even if you don't care about the expansion of the universe, even if you don't care about dark energy, you don't care about supernova, you just care about looking at the galaxies that were produced by Darren Crotton's simulations. Okay, but in his simulations, what happens is the expansion has a role, a very important role, right? So when you write the equations that you do the n-body simulations on cosmology, you have to put all this, because you have to put all the expansion rate, which changes the growth of structure, which will change the results. So even if you only care about the galaxies at the end, that's what goes into your calculation, right? That's why we are discussing this. An exercise also, if you, after having some beer or caipirinha this night, take P equal W rho, you can solve this very easily, 2 lines. You can solve this with K equals 0, 2 lines, and you'll be happy that even drunk, you can get the solution of a universe with P equal W rho. Okay, so I said this, we can skip this. And as I said, the evolution of each component is different, and also the fraction of the universe that depends on each quantity will change with time. So if I write the Friedman equation, and if I write the density really as a sum of the densities of all the components, what you see is that very early, when A was very small, basically what was giving the dynamics of the universe, the scale factor as a function of time, was the radiation, right? So when I go very early in time, as this decreases very fast, so this is the blue line. This decreases very fast, right? A to the minus 4. When I go early in time, this was clearly dominated. So the early universe was dominated by radiation. The dynamics of the universe was given by radiation. And this has a lot of implications for structure formation. For example, the fluctuations don't grow during this period. So you don't form the seeds for galaxies when you are radiation dominated. Then you have matter, like ordinary matter, and this goes 1 over a cubed. And if you have something that has a W smaller than minus a half, for example, cosmological constant or dark energy is -1, so it's a constant, then all things will go down and the cosmological constant or dark energy will stay. So here's what we live nowadays in a universe that's mostly composed of this thing that goes with time slower than matter and slower than radiation. And if you look at the history of the universe, you have a radiation-dominated time where the dynamics of the universe is given by the radiation. You have some matter-dominated time where the dynamics of the universe is given by matter. And it's during this time that most of the structure is produced. Because we will see, or I will mention, that when the universe is really dominated by dark energy or cosmological constant, the structure, the growth of structure is smaller. So the period that's relevant for galaxy formation is a matter domination. There is a people usually say that there is a coincidence problem because now two-thirds of the energy density of the universe is in the form of, let's say, dark energy, and only 1/3 is in the form of matter, right? But when the universe was half of this size, you know, the difference was 1/8. Was way larger, right? When you go down in time, the difference between the matter and the cosmological constant is very, 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 very big, right? Why these are so comparable today? So people call this a coincidence problem. They try to find a dynamical explanation for these two quantities, dark matter and dark energy, being comparable nowadays. But there is another coincidence problem that's connected to K, because K seems to be really small. If K wasn't small, and as I said, K is connected to the curvature of the universe, if K wasn't small, we would have some curvature-dominated time. You only don't have because this thing is smaller than 10 to the minus 5. But why? People are crazy finding explanations on why the dark energy has the value it has, but no one cares about the size of the curvature, right? One of the reasons is if you use a theoretical prejudice that the universe has an inflation, this K is really small, and you know why. It's because of inflation, right? Okay. Yes.
So I actually have a question on this coincidence problem. I understand that the one with the curvature, but I've always wondered about the coincidence with respect to dark energy and the other components. It seems like, okay, you can think in terms of, in absolute terms of 2/3, 1/3, but at the same time, in terms of time, it's a coincidence spanning like 5 billion years or so within a 13 billion year universe. So is it really that hard to assume it's?
People like to see it in logarithmic time. So in logarithmic time, it makes a big difference, because so if you look at all these times in the universe, I don't know, nucleosynthesis, radiation dominate, and so on. If you put them on a log, you'll be able to compare. If you put on a linear scale, everything that's early universe, even the CMB, it's 300,000 years. So I don't know. It's a human argument. It's not a physics argument. People like to sit in log time, and in log time it makes a big difference. But I agree that in looking linearly in time, yes, most of the time the universe has been dominated by I mean, the point is, the real point that makes sense is that you cannot have a universe that was dominated by dark energy without having a matter-dominated period. That's what you need to have us here. So that's the only real thing. More questions? Okay, so to be able to understand these plots that the cosmologists show all the time with these level curves and omegas and so on, let's do this. we'll redefine the quantities here, because density here, you know, density of the universe is 10 to the minus 28 grams per centimeter cube. It's a really tiny thing. And you don't put the grams per centimeter cube when you're doing codes. Your numerical codes, they just work with numbers. So we always like to have things that are non-dimensional, you know, for practical uses, but also that they have orders of magnitude of 1 and not 10 to the minus 28. So, and it's really useful to understand. It's not just a statical thing. So let's divide the density here by some density that's called critical density. That's the density for which this k equals 0, okay? So if I measure the expansion rate today, I will tell you, oh, I know H naught. So you can tell, so the density is H naught squared over 8pg times 3, right? This is it. So if I have a very natural energy density reference, which is made out of just assuming k equals 0, and that gives you this energy density. That's what we call critical density. Why critical? Because it's what divides a universe that has positive and negative curvatures, as we will see tomorrow. So we divide by this critical density, and we call this the omega parameter, right? So if a universe has only one component, and the little rho is higher than the critical, then this omega is more than 1. If it's smaller, this omega is more than 1. But we also write some omega associated to this k, 1 over h naught squared, okay? So you can work out that the sum of these omegas with this one has to be 1, right? And we can write this Friedmann equation, which seems like a complicated equation. We write it in a very, very, very simple way. The h, which we'll see, is the expansion rate of the universe. So the expansion rate of the universe is connected to some initial reference value, which will take it as today. So h naught is the expansion rate today, as compared to these quantities. So the omega associated to radiation, and the scaling is the scaling with the scale factor that you know. The mass, and the mass with the scale that you know. This omega k has 1 over a squared, right? And lambda, let's assume now it's a constant, so dark energy is constant, will give you this expression. So you have a very simple expression of the expansion rate of the universe in terms of everything that goes into. And the sum of all these, including k, has to be 1, right? So omega k is 1 minus the sum of all other omegas. Okay, I think, okay, let's try to proceed a little bit, but I'm about to stop. Yeah, no, I think it's better to stop now, so we have time for questions, and we'll start tomorrow making this connection of the model that we are building, because we are actually building a model, right? We assume the universe was homogeneous and isotropic to achieve the Friedmann equation. We assumed energy conservation to have the energy conservation equation. We assumed that the different components didn't interact, and only through this we wrote some equations that give the expansion rate of the universe as a function of all these quantities that are connected to the abundance of all the components of the universe, right? So tomorrow we'll see how these things compare, for example, with the expansion rate that we observe with the redshift. So, questions? Thanks.
So, thank you, Martin. Do we have any questions? I think people were asking during the... No?
Hello. It is actually something about what you mentioned about gravitational lensing affecting the background radiation as well. This is something I have never thought about. Does this matter, or do we use the background radiation, the only information we need from it is that the temperature and that it is inhomogeneous? Do we use anything else from it that would be affected by the lensing, or the lensing doesn't matter?
Yeah, so it does measure, and we do measure it. It does matter, and we do measure it. The strongest distortion on the cosmic microwave background comes from very massive objects, let's say galaxy clusters. So the angular scale of these objects is really small. So when you look, probably you've seen a plot like this, and I'll show the plot tomorrow. But probably you saw a plot like this that shows the amplitude of the fluctuations, some called CL. So CL times L plus 1 is just a normalization as a function of L. So this L, you know, is probably saw this you decompose in spherical harmonics. This L is the L of the spherical harmonics. So basically this tells you the scale and the amplitude of the fluctuation as a function of scale. And what you see in the SMB is something like that, right? Tomorrow I'll devote quite some time in interpreting this plot and why this peaks and so on. But what I tell you here is that for very large L means very small distances, right? So the lensing does not affect this region at all, but it does affect here, and we can use this fluctuation in small scales to measure the lensing. Just to make some publicity of this survey in CS82, there's a high resolution map of the CMB in this region of the sky, so we could measure the CMB lensing, and we could correlate this with the lensing of galaxies. So we have an idea of how the structures evolve so we have structures all between us and the CMB, right? But we can see the differential effect on lensing of all the scale from all the structure from us to the CMB, and the nearby scale of galaxies that are not that far away, and so we can compare a little bit of lensing with a long of lensing by comparing these two things. But I won't mention this tomorrow. Does it answer your question?
Hi. I have a question regarding the lambda CDM model. So it has two problems: the missing satellite problem, and also the particle associated to dark matter would be a problem. How do you think we are going to solve these two problems in the future?
Okay, so for scientists, problems are solutions, right? When we get problems, we get excited because we can do new physics. So I would like to discuss about these small scale problems tomorrow, but since I'm not 100% sure, I will try to answer your question today. So in small scales like dwarf galaxies and satellite galaxies and so on, satellite galaxies than predicted by the standard lambda CDM model. So you have a shortage of fluctuations in small scales, right? So that's a problem, a possible problem of the cold dark matter, right? The question is whether this problem is real, so these structures are not there, or whether we don't see them because they don't have stars, for example, right? So a way of measuring the substructures is to look really in the lensing, because you may not have the satellite galaxy, but you may have satellite clumps. And if these clumps are there, but not the galaxies, then you say, well, not a problem of dark matter, it's a problem of your galaxy formation, the stars, and you don't understand this physics. But it could be on the contrary, that these matter fluctuations are not there, they are not these small halos, and then you can say, well, there may be a problem on the dark matter itself, or there may be a problem of the simulations. Sometimes I don't put all the physics of gas stripping and I don't know what, of feedback by IGN, supernova, etc. So there may be a way that I don't have these fluctuations, but for some physics that is not included in the simulation. But now, for the moment, let's take at face value these problems. So let's think really that they are missing this, the missing satellite and all this missing substructure is a problem. Let's say that even if I put all the physics, it should be there. I look at this weak lensing, it's not there. So then what, right? Two possible solutions are warm dark matter and self-interacting dark matter, right? Self-interacting dark matter may be very heavy, but it does have a self-interaction cross-section. And one of the ways of testing this model is with the colliding clusters, right? So there are constraints on the maximum self-interaction rate. And so you said this is maybe a problem for physics, right? So I said, no, physics are very happy because they know that the standard model of particle physics is not the final word. This is for sure. I mean, it's like when I say that gravity must be in agreement with quantum theory, because it's just a matter that the nature is quantum. for the similar reason, particle physics know that the standard model is not the final word. So they look at theories beyond the standard model, and many of them, they predict stable massive particles, which could be dark matter particles. So there was a whole workshop on dark matter 2 weeks ago in São Paulo, and it's amazing the zoo of dark matter particles that the theories produce. So I won't say it's a problem to the theories. On the contrary, they are very, very happy because they can do very, very different theories. And basically, for each problem that you give you, I'm sure they will give you a candidate that solves the problem. So it just shows the richness of this interaction between finding cosmological problems and look at fundamental physics. So that's, I think, the big interplay. So, I mean, just not to enter in the details, but as you said, for example, if you have self-interacting dark matter, you have to have a mediator that interacts, because all the interactions that we know in particle physics, they have mediators. So you have a mass of a particle, now you have a mediator. But, I mean, within particle physics, this is, it's easy to deal with. We don't know just what is the right theory. So one nice thing about cosmology now is that it tells you about new physics that is not necessarily guided by physics experiments in the accelerators, but that is found first in the space. So this could be one of the things. If we find that dark matter is self-interacting, they have an answer. But it would be us telling them what kind of particle is it, or more dark matter. So I would say that the small-scale problems, I'm not fully convinced that's a problem, but if there is, as far as I understand, you can solve it with different dark matter particle properties. So I don't think it's a problem for the dark matter, right? Does it answer your question?
More questions? So let me just finish with one. I would like your opinion. It seems to me like dark matter is very much standard. It's hard to. Some people like to use alternative theories like Mon and that kind of thing, but those are getting harder and harder to accept due to the data that we have. And to some extent, even dark energy, maybe a little less so, but combining all the information that we have from CMB and supernovae, for example, at least the cosmological constant works very well to a degree. So what do you think about alternative theories, both in dark matter and dark energy? Are they still a good candidate, or should people abandon them at some point? What do you think?
Okay, your question is very human. It's not very scientific, because it's like when humans decide that they should stop trying things, right? So I remember exactly 10 years ago, I was discussing with Zofer Lahav, which is a known cosmologist, and about exactly the question that Thiago says. Like, okay, as I will show during the lecture, everything that we know agrees with a cosmological constant being the solution for dark energy. So a single number explains everything. So we should be really happy. The problem is physics wants to have an explanation for this number, and that's where dark energy goes in, right? So at what moment will we be happy and just stay with lambda? When we know lambda to which precision, right? Millions and millions of dollars go invested in the next generation dark energy experiments that they try to measure exactly the quantities they introduced to you today, like W, parameter of P over rho, so it's the equation of state parameter. So there are a lot of experiments that are willing to measure W better and better, and W not, how this fraction P over rho changes in time for the dark energy. And of course, omega dark energy, omega lambda. So a lot of effort and money is going to that, but it's always compatible with W equal -1, W not equals 0. When will you say, you should give up? People modify, have very weird theories for scalar fields and so on. They modify gravity with f of r theories, with Rondeski, beyond Rondeski, and very complicated Lagrangians trying to explain this. And at what point people will give up and say, well, maybe it's just lambda? I don't know. I mean, I can answer you very personally, but this is really a matter of taste. So I gave up. I'm not looking for W anymore. I mean, that's not my main interest because I think, well, I got tired about that. But I'm not against investing millions and millions of dollars in experiments trying to measure W. First, because, as I said, it's just a matter of taste. So I don't have the truth. But secondly, because all these surveys have so rich information on everything in astrophysics that it doesn't matter if it's lambda. This money doesn't go to a wrong place. It's used for doing good astronomy. So maybe people are looking for one thing, explanation on lambda, they find many other things. So, but personally, I give up, and in the dark matter also. Like, of course, we never ever have the final word in science, right? There's not infinite truth. So it could be that there is no dark matter and there is modified gravity. It could be. But my personal opinion is that it's such an overwhelming number of different data with different natures points to a particle-like thing. And physics seems to accommodate this particle-like thing in such a simpler way than modifying gravity that I would, my personal choice, be dark matter. So I would say dark matter and lambda. But of course, we are all here to challenge this. Observationally, trying to find, results that disprove what I just said, and trying to find alternatives to maybe modify gravity, But I'm being very assertive here, very strong, although I know that we cannot, be 100% sure. And that's a personal feeling, that in Brazil, we usually spend more time doing non-standard things than the standard things. So we always want to revolutionize everything, and sometimes a simple calculation, gets you to something new because I'm proposing a new theory. And we don't look into the things that are more, let's say, standard, but that take a lot of work, and they give you more results that are sometimes more relevant. So it's since this is a school, I think there is something connected to our idiosyncrasy that we always like to be divergent. How we call, there is a name for this. Well, I forgot. So let's, all the energy that we want to be against the system, let's use against the political system, and, and then let's keep doing science.
It's good that you touch upon dark matter, because I wanted to have a provocative statement like him. One can keep believing in it, but people keep not finding it. And it's 20 years on over that billions of dollars, or millions maybe, are being spent for experiments, and they keep being unsuccessful. And you say it's overwhelming and we don't find it. And why is that? Because at some point one becomes skeptical.
That's a very good question. So there are standard models for dark matter, like the most standard is a cold dark matter WIMP, a weakly interacting massive particle, so like a supersymmetric particle. So we can make predictions of the cross-section of these things, and all the detectors know the sensitivity fact that are below or very below. There's not so the fact that we don't detect yet, it's not a problem. Even for the most standard dark matter, I don't think it's a problem, really. I like to make the comparison with gravitational waves, because I was really skeptical. Gravitational waves, the general theory of relativity is a very successful theory, and we believe in it a lot, maybe more than supersymmetry. So people were more, there should be gravitational waves. But, I'm older than most of you, so I've been seeing a lot of these gravitational wave experiments, not many of them, but many generation of them. And they were always saying, we'll detect gravitational waves in the next generation, and they didn't. We'll detect gravitational waves in the next generation, and they didn't. So I thought, well, maybe they will never detect these gravitational waves. And I just, didn't follow the subject until, you all know, this guy said, we detected gravitational waves. We did it. This sentence is here in my mind. And always that I remember this, I cry, as you see, because I think it's so fantastic. So, I was skeptical, and they detected gravitational waves. So I would say, I cannot guarantee they will detect dark matter, but I don't think we're in a moment that we say, well, we did not detect dark matter, then what? Because on the one hand, I don't think we're sensitive enough to rule out the most standard models. And secondly, because, it's not like GR that's a single theory with a prediction. There are many, many different models. It could be that dark matter doesn't have the weak interaction. Or virtually mostly all the detectors of dark matter, they rely on the fact that dark matter has a weak interaction, like a neutrino. But it can just not have it. It may just have gravitational interaction. and then none of these detectors will detect, and doesn't mean that it doesn't exist. But now the particle physics came up with interesting models of some dark matter particles that may not have the weak interaction and still be detectable. So, I mean, there's lots of things to happen. So I don't think we're at the point of saying, well, we have not detected in the lab, so what? I think people are getting very excited about lab detection because they think they are reaching, you know, they are already probing the parameter space, for example, of supersymmetric models. So yes, they can rule out parts of this parameter space, and they are very happy, but they haven't ruled out everything, and if they do, maybe it just means that dark matter is more complex, and people have models for this. So I don't know if that answers your question.
Okay. So if we don't have any more questions, let's thank Martin again.
Thank you.
Any announcements? So just coffee break, food,